Kia ora koutou katoa. This is a video for NCEA Level 2 Chemistry, and it's about the reactions of alcohols. In this video, I'll talk about the oxidation of primary alcohols, substitution reactions, elimination reactions, and combustion reactions. Primary and secondary alcohols can be oxidized using oxidants such as acidified dichromate and acidified potassium permanganate. Potassium permanganate is a purple color and it is a strong oxidizing agent. It will also oxidize alkenes. Potassium dichromate will not oxidize alkenes. Primary alcohols are alcohols where the hydroxyl group, this hydroxyl group, is attached to a carbon that is attached to only one other carbon. So primary alcohols have the OH group at the end of a hydrocarbon chain. So therefore, they oxidize to carboxylic acids. This is the carboxylic acid group with a double bonded oxygen and a hydroxyl group. Sometimes you can see this indicating an oxidizing agent. In this case, we could either use potassium dichromate, and we say it's acidified, so we have H+, or potassium permanganate, also acidified. Potassium dichromate, or in this case, I've left off the potassium, and I've just written the dichromate ion and the permanganate ion. Dichromate is orange, and it changes to green when it's reduced, and potassium permanganate goes from purple to colorless. Both these reactions produce color changes. So dichromate, as I mentioned, goes from orange to green, and permanganate goes from purple to colorless. Secondary alcohols are oxidized to ketones. Ketones do not have a carbonyl group, a double bonded oxygen in the middle of the hydrocarbon chain, not at the end. This is covered in Level 3 NCEA Chemistry. Tertiary alcohols do not react. They cannot be oxidized. The oxidation of dilute ethanol to ethanoic acid, also called acetic acid, can be done by the acetobacter bacteria, and this is how vinegar is produced commercially. Another reaction that alcohols undergo is a substitution reaction. This is when the hydroxyl group of an alcohol molecule can be replaced by a halogen atom to form a haloalkane. There are three possible reagents, these three here. So we've got phosphorus trichloride, phosphorus pentachloride, and thionyl chloride. You can use any of these reagents on an alcohol compound to make haloalkane with a chlorine atom. So the hydroxyl group gets replaced, substituted for a chlorine atom. The next reaction we're going to look at is the elimination reaction. An elimination reaction is when a carbon-carbon double bond is made. When an alcohol is heated with concentrated sulfuric acid, a water molecule is removed or eliminated and an alkene is formed. The hydroxyl group and a hydrogen atom from a carbon atom adjacent or next to the carbon atom bonded to the hydroxyl group are removed. So in this case, in this example, we've got ethanol, and these are the two atoms that are going to be removed to make H2O over here, water. They need to be next to each other on adjacent carbons. So we're going to use concentrated sulfuric acid, heat, and we're going to use an excess, and it's going to be an elimination reaction to form this carbon-carbon double bond. So elimination is taking something off and forming a carbon-carbon double bond. Now, if that alcohol is an asymmetric molecule, then there are two possible products from this elimination reaction. And in this example, we've got butanol. We're going to look at these two carbons here, and these two carbons here. So they are next to the carbon that has the hydroxyl group on it. So that one makes the major product. And this combination makes the minor product. Over here, but-1-ene. The same rule applies as for haloalkanes that undergo elimination reactions. The hydrogen atom lost is removed from the carbon atom containing the fewer hydrogen atoms. We remember it by the poor get poorer, but we need to explain it with a sentence, not just the poor get poorer. Okay, so the major product is but-2-ene because I just get rid of this here. Why is but-2-ene the major product? You have to be able to explain it. So this carbon here has the hydroxyl group, and it's got two possible carbons, this one or this one that it could form a double bond with. This carbon here has 3 hydrogens attached to it, and this carbon here only has 2, so it's asymmetric. So it'll form the double bond here much more likely because this carbon only has 2 hydrogens, so it is more likely to lose another hydrogen. So it's going to form the major product, which is but-2-ene, and the double bond will form between carbon 2 and carbon 3. This is compared with the minor product, which is the double bond forms between these two carbons here, carbon 1 and carbon 2, forming but-1-ene, and we still lose the hydroxyl group and hydrogen, but that is just less likely to happen. But you do get 2 products. The next reaction is combustion. Alcohols are very good at burning in air very cleanly. We use them, there's cars now that will run on ethanol. In the same way as hydrocarbons, they burn with oxygen. We call that combustion. So we want, for complete combustion, you need excess or lots of oxygen. And so combustion is the reaction of this alcohol with oxygen, and it forms carbon dioxide and water. That's always the products from complete combustion. So solubility and oxidation of alcohols. So we did this reaction and we just added a few moles of ethanol, and we found that the potassium dichromate went from orange to green, and the potassium permanganate went from purple to colorless, and ethanol was soluble. It didn't form 2 layers. And so that's the end of this video, which is about the chemical reactions of alcohols: oxidation, substitution, elimination, and also we covered combustion. Thanks for listening.